Now let's talk about how to evaluate how well our fitted model fits the observed data. So there's many different ways that you can assess goodness of fit, but we're going to talk about one specific one that's pretty frequently used. And the goodness of fit is denoted by R squared, and it's called the coefficient of determination or the percentage of variance explained. And the way that we actually compute R squared is that it is 1 minus the ratio of the residual sums of squares over the total sums of squares, which is equivalent to the regression sums of squares over the total sums of squares. Another way of computing it is that it is the squared correlation between the observed data and the fitted values. So you compute the correlation between the responses and the fitted values, and then you square that number. Of course, this sort of begs the question because we haven't defined the total sums of squares or the regression sums of squares. So let's just do that right now. So TSS, the total sums of squares, is the sum of the squared deviations between each response and the sample mean. The regression sums of squares is the sum of the square difference between the fitted values and the sample mean. And in fact, you can show that the regression sums of squares is equal to the total sums of squares minus the residual sums of squares. Or another way of stating that, the total sums of squares is equal to the residual sums of squares plus the regression sums of squares. So let me actually just draw a picture to kind of show you what these different things represent. So we had some data, and we fit our line to it. Actually, I shouldn't do that. So for the total sums of squares, actually, you're comparing it to the sample mean. And so the total sums of squares measures the vertical distance between each response and the sample mean and squares that distance and adds them up over all observations. So this is total sums of squares. We're summing the square deviation between each response and the sample mean. The residual sums of squares, on the other hand, if we had the same data set and we fit the line to it, the residual sums of squares measures the vertical distance between each response and the fitted line, and we sum those squared residuals. So that's the residual sums of squares. And then the regression sums of squares is somewhere in between those two things. So we have this data set, same data set presumably, and we have our sample mean, and we have the fitted line. And so what the regression sums of squares does is it actually measures the distance between the sample mean and the fitted value for each observation, squares that distance, and sums over all possible observations. So the regression sums of squares is the sum of the squared distance between the fitted values and the sample mean. And so these are just different ways of quantifying the fitted model. And so let's talk a little bit more about the interpretation of these. So the total sums of squares is measuring the amount of variability in our responses in comparison to the sample mean. And in fact, the total sums of squares has a relationship to the residual sums of squares in that the total sums of squares is equal to the residual sums of squares for a constant mean model. So if instead of having an intercept and a slope, we only had the intercept, the residual sums of squares for the fitted model of this type would in fact correspond to the total sums of squares. So then what does the residual sums of squares measure? Well, that's the amount of variability in our responses that is not explained by our regressors. Let's go back to this picture right here. Okay, and so here's our fitted model using our single regressor variable x, and the residual sums of squares is trying to quantify how much unexplained error there still exists in the model after accounting for our regressors. And the regression sums of squares is really measuring how much variability was explained by our regressors in comparison to the constant mean model. So what we're doing is we're looking at the results from the constant mean model, we're comparing it to what they are for our fitted model, and we're quantifying how much additional error was explained by adding the regressors to the model. And when you compute R squared, you're always going to get a value between 0 and 1. It's a true proportion. And in general, values closer to 1 indicate that the model, the fitted model, fits the data better. However, that does not necessarily mean that useful prediction can be made or that in fact the model is a very good fit. So there's crazy things that you can actually do with R squared, so we'll learn more about this later. But let's just say that we had the responses and we'll plot them versus the fitted values. You can actually, if you add enough regressors to the model, you can get a perfect fit, in which case your R squared would equal 1. But in fact, this is probably not a very good model because it probably means that we have overfit the data. So if this was our data set and we had a single predictor variable x, or a single predictor x, and a single response y, you could actually get a model that looks something like this. And you might say, oh great, that's a fantastic model, it perfectly fits the data. But in fact, this is overfitting because if we wanted to make a prediction at some point in this data set, let's say we wanted to make a prediction over here, this line extends down here, this would be our prediction, when in fact, looking at the data, the relationship probably looks more like that straight line. So we don't want to overfit. So just having a large R squared is not necessarily an indication that the model is in fact a good fit, though in general we do desire to have a larger R squared value. And conversely, actually, a small R squared does not mean the regressors are unrelated to the response. So R squared measures whether there is a linear relationship between the regression coefficients and the response. In fact, it's possible that there's some other relationship and the regressors we included just really aren't capturing that relationship. So for example, if this was my x variable, this was my y variable, and let's say that this was our data. Okay, if we fit a straight line to that, maybe we get something like that or like this. Our R squared value would be extremely small, when in fact, there's a very strong relationship between the response and our predictor variable x. We just haven't added the proper regressors to the model. So a large R squared does not necessarily indicate a great fit of the data to the model or of the model to the data, and a small R squared doesn't necessarily mean that the regressors are unrelated to the response. You might just need to add different regressors to the mix. So here's a sort of visual conception of what R squared is trying to measure. So this big set of arrows here sort of measures the total amount of variability, and the dashed set of arrows here is measuring how much variability there is in the errors, and the remaining amount of variability is how much is actually explained by our regression model, and that's what R squared is trying to compute. So how much additional error did adding the regressor variables improve our model fit? So here's some examples of some different data sets that I generated. And my question for you is, what do you think R squared is going to be in these following examples? So with the idea that a small R squared is going to be a poor fit, a high R squared closer to 1 indicates a good fit. So why don't you pause this video for a minute or so, look through these different data sets and see whether you think that R squared is going to be small or large. Okay, now that you've had a few minutes to look at these examples and try to figure out what values of R squared are large, which ones are small, we'll talk about them together. So in this case, we see there's a lot of variability around the fitted line here. And so this would be a situation where R squared is probably going to be pretty small because this line is not really that close to the observed data points. In other words, there's still a lot of unexplained variation in the response that our single regressor variable couldn't help us with. So this probably has a small R squared. Whereas in this example right here, we see that this line looks very close to the responses. And so there's not a lot of unexplained variation. And so we expect R squared to be high. In this example right here, you can almost imagine there's a little bit of a curve here, so maybe we should actually be fitting a quadratic. But overall, this straight line doesn't fit too terribly poorly. So it definitely looks like this line is closer to the observed data points in this graph over here. So R squared is probably not going to be really large right here, but it's going to be larger than the first graph. Whereas with this last one, we can see that there's actually a very strong relationship between the predictor variable on the x-axis and the response, but it's not captured by a straight line. And so we would expect that r squared is going to be very small here. And so if we actually compute the r squared values, which I will show you how to obtain shortly, we'll see that they're 0.007, or I guess 0.008, very close to 1, 0.6, and then something that's pretty close to 0 respectively. So this had a small r squared, this had a small r squared, this had a very large r squared, this was sort of moderate in the 0.6 range. So in general, the closer that the fitted line is to the observed data, the larger the r squared value is going to be. So where can we find the r squared value, the coefficient of determination, for a fitted model? There's actually a few different ways that you can do this. Maybe perhaps the easiest is just to use the summary function spelled correctly or the summary function spelled incorrectly. That's available in the Fairway package. And if you look through the resulting output, then you will see something called multiple r squared or r squared. And that's going to correspond to the r squared that we've been talking about. So for that first model that we fit, we get an r squared of 0.01. So kind of rounded it there. The other option is that if you can actually directly extract it from the summary function. So if you fit the summary, if you use the summary function on your linear model and then use $r dot squared, that would extract the exact r squared value from your fitted model and print it to the screen. So we can see a couple of different ways here to obtain the r squared fairly automatically from r. So one of the things that I have to emphasize about the definition of r squared is that it only makes sense if our model has an intercept in it, since the null model it's compared to has an intercept itself. So if your model doesn't have an intercept, then computing r squared directly is actually going to give a misleadingly high value. So how can we compute a measure of model fit when our model doesn't have an intercept? So in fact, there's a very easy thing that people commonly do, and that is that we compute the squared correlation between the responses and the fitted values. This doesn't require that we have an intercept in our model, but it still measures how closely our estimated mean is to the true responses. So if your model does not have an intercept, then instead of computing the r squared directly from within r, you want to compute the correlation between the response and the fitted values and then square that number. Now one of the things that's going to come into play fairly soon is that we need to talk about the degrees of freedom. So every statistic, something that you compute from data, in fact has degrees of freedom. And generally, when you talk about degrees of freedom, this is the number of observations in your data set, which we denote by n, minus the number of parameters that had to be estimated along the way in order to compute the statistic. For the total sums of squares, so I'm going to go back to that formula right there. Okay, we actually had to estimate the mean in the process of computing the total sums of squares. And so the total sums of squares has n observations minus one parameter estimated along the way, and so we have n minus 1 degrees of freedom. The residual sums of squares has n minus p degrees of freedom, since we have n observations, and then in order to compute our residuals, we actually have to estimate beta naught, beta 1, up to beta p minus 1. So we have to estimate the p regression coefficients. So the residual sums of squares has n minus p degrees of freedom, the number of observations minus the number of parameters that we had to estimate along the way. Lastly, we talk about the regression sums of squares. So the regression sums of squares has p minus 1 degrees of freedom. So I can't clearly articulate why this is the value for the degrees of freedom as I could in the previous examples, but the n minus the number of parameters to estimate is going to result in p minus 1 degrees of freedom. So as we conclude this section talking about goodness of fit in r squared, I want to emphasize the fact that you cannot rely alone on r squared to diagnose how well your model fits the data. A famous data set that illustrates this point is called Anscombe's quartet. And this guy named Anscombe, this researcher named Anscombe, generated 4 different data sets. They look very different when you plot them, but in fact, their intercept, their slope, and their r squared values are almost identical. So they're not exactly the same, but they're very, very close. And However, if you look at the fit of the model to each data set, it's very clear that in some cases the model fits the data well, in other cases it fits poorly. And so you can't just blindly use R squared without evaluating whether the model actually fits well graphically. So here's a picture of the Anscombe's quartet data sets. So we have the first data set, the second data set, the third data set, and the fourth data set. You can see for this first data set, it looks pretty typical. There's no outliers or anything. And though the model doesn't fit the data perfectly, it still fits the data reasonably well. On the other hand, for the second data set, we see this sort of quadratic thing going on. So it doesn't extend down to the very bottom here, but there seems to be a clear relationship between the x variable and the response. If we put a straight line to that, we can see that there's some very important characteristics of the model, or I should say of the data, that aren't being captured by the model. So really, we should be fitting some sort of curved model to this data set, and so a straight line is really not adequate, and yet the R squared value for this model right here is identical to the fit for this model right here, even though clearly this model right here is more appropriate than this one. For this data set right here, these points are actually in a perfectly straight line. The only one that's different is that this next to last observation here jumps up. And so we have this fitted line here, which sort of gets pulled by this outlier in the vertical direction. And this would be a situation where perhaps we should use a robust linear model. Maybe we should downplay the importance of this outlier. The line should be closer to these points down here. But once again, the R squared value for this data set using this fitted line is exactly the same as this model and this model. And then lastly, we have this data set right here where these are all actually vertically oriented. So these are just dots stacked one on top of the other. And we have this one outlier over here where we have a different x value. And so there's really no reason to think that this model fits the data well at all, or that it accurately describes the relationship for this data. But once again, the R squared value is identical to the R squared values for these other data sets. So once again, you can't just blindly compute R squared and then use that number and assume that it accurately reflects how well the model fits the data. So before you interpret R squared, you should actually plot the responses versus the fitted value. And if you look at a plot of the responses versus the fitted values, and it looks approximately like a straight line, then R squared is a meaningful summary of how well the model fits the data. If it's not a straight line, then that is evidence that in fact that our model is not adequate, that maybe we need another regressor, or maybe we need to remove a regressor. And so this is an important diagnostic tool that you should use before you interpret the R squared value. So let's just look at a few data sets right here. And I want you guys to pause this video for a second, and I want you to assess whether you think R squared is a meaningful measure in each one of these data sets. Okay, so probably that didn't take you too long to do. So once again, when we plot the response versus the fitted values, we want the scatter plot to look approximately like a straight line. And so when we look at this right here, this data set kind of follows in a straight line, so R squared is probably meaningful here. In this case, we can see that the model is probably not a very good fit, but there's no clear curves or anything like that. So even though we don't see a clear linear trend, we don't see any clear violations either. So R squared probably is meaningful here. It's just an indication that the model does not fit the data very well. In C here, there's a very strong linear pattern running from top to bottom, going left to right. And so here's another situation where R squared seems to be a meaningful measure of model fit, whereas really in these last three graphics, R squared is probably inappropriate. So when we plot the response versus fitted values, we see a clear curving relationship right here, which means that there's really the mean structure of our model is incorrect. So we actually need to fit a different model here. But if you just looked at R squared, you may not necessarily know that. In this case right here, it seems like our model is completely driven by this point over here. So there's no real relationship between the response and prediction over here, which makes us think that there's not a very strong relationship, or I should say our model does not fit the data very well, or at least is not very useful for prediction. And it's just this one outlier that's sort of causing it to look like maybe it's a good fit. And then lastly, with this one right here, it's interesting because as we move from left to right, we see this pattern going from bottom to top, where there is sort of a straight line with these points. But what it actually looks like is maybe we should be fitting 5 separate models in a sense to this data set. So there's probably some other variable that's causing this data to clump in certain ways. So even though we actually see this sort of linear trend in one way, there's still an important pattern in our data that is not being captured by our model. So this plot right here would indicate that we actually should be fitting a different model to the data. So as we conclude this section here, not everyone likes to use R-squared as a measure of model fit. So I'm going to throw out another measure, though it's not nearly as useful in general, and that is actually just computing the estimated standard deviation of the errors, sigma hat, which is just the square root of the residual sums of squares divided by the residual degrees of freedom. And in general, the smaller sigma hat is, the more variability that's explained by our model. So I'm going to go back to a plot we saw earlier right here. So when this arrow is smaller, relatively speaking, that means that sigma hat is smaller. And if sigma hat is smaller, that means that more variation in our responses has been explained by our regressors. So in general, we want sigma hat to be smaller, relatively speaking. But you may have noticed I keep mentioning the word relative. So the size of sigma hat is relative to the size of the responses. So if I said that sigma hat was equal to 6, you wouldn't know whether that was a large number or a small number. And because sigma hat is not unitless, which R squared is, it's actually difficult to determine whether sigma hat is small or large. And so while some people use it as a measure of model fit, it's difficult to interpret, and so it's not something that people use on a frequent basis.